Hey guys, this is Lab 5, Collision, for Physics 2211. So in this video I'll go over the introduction, the purpose of our lab, some formulas we'll use, the experiment and data, our glow script and model, discussion of possible errors, and our conclusion. So the purpose of this lab is to analyze a one-dimensional collision between two equal mass carts. Then we'll use Tracker to analyze the position of each of the carts and then create a glow script model to predict the motion before and after the collision. Some things we'll visit in this video is the momentum principle, Newton's second law, kinetic energy, and collision type and energy loss. So the momentum principle. The total momentum of the system should remain approximately constant during the collision if external forces are negligible. Newton's second law. Newton's second law helps describe how forces change an object's motion and supports the computational model used for carts. Kinetic energy. Comparing kinetic energy before and after the collision helps determine whether the collision was elastic, inelastic, or partially inelastic. Collision type and energy loss. We want to know if the collision was elastic, inelastic, or partially inelastic. Some formulas we'll use are the collision relations here, and then some assumptions we'll make for our model is cart A is pushed, then moves toward cart B on a nearly straight track. Cart B is essentially at rest before the collision. The best fit before impact is taken from a short time window, not the full run, and a small slowing term after impact improves the long-term fit for cart B. So here's our tracker where I observed the motion. I uploaded the video to tracker and plotted the observed motion using AutoTrack. I recorded the positions data for cart A and cart B and exported the tracker data as a CSV. I used the tracker's data to estimate the cart's initial positions and use their velocities before and after the collision. And I used those values in GlowScript to model the motion and compare the predicted results to the experimental data. Here's our motion.
Go. It did not go out of frame, did it?
Here's the GlowScript code analysis. So our system is the Earth, mass A, mass B. Our surroundings are none. I first set up the simulation window and view. I defined both cart masses to be 0.475 kilograms. I used tracker data for the cart starting positions. I set cart A speed before the collision and cart B at rest. And I defined the collision time. I included two model options, ideal elastic collision, improved model collision, and then improved model based on real data. The initial position and velocity was found using the first two time steps. So here's the masses, our acceleration in the x direction for both A and B during the start, our velocities for A and B both before the collision, and then the time of the collision is right here. Here I created the track and both carts. The red cart is cart A, cyan cart is cart B. It adds motion trails for both carts, creates a position time graph, and creates a velocity time graph. Here are some initial conditions that I kept. I said I set cart A's initial velocity, and then I kept cart B initially at rest, and then I found it prints the time and position of velocity values for later computation. Here I run the simulation until 3.55 seconds. Before the collision, cart A moves at a constant velocity, cart B stays still. After the collision, cart A nearly stops, cart B moves forward. In the improved model, cart B slowly loses speed after impact. It updates the cart's position after each time step. It updates the trails and graphs during each loop, and it prints the predicted values for spreadsheet or graph comparison. Here are our graphs, and here's my model. Some sources of error would be human error for picking inaccurate tracker positions. And since it's not an isolated system, the cart will experience wheel friction, vibrations, sounds, and other tiny deformations. So what if the collisions had been perfectly elastic, or what if the carts had stuck together after impact? If the collision had been perfectly elastic, then because the two carts have equal masses, cart A should have stopped almost completely after the collision, and cart B should have moved away with nearly the same speed that cart A had before the impact. In our experiment, cart A did nearly stop, but cart B moved away with a speed close to but less than cart A's original speed. This means the real collision behaved somewhat like an elastic collision, but was not perfectly elastic. On the other hand, if the carts had stuck together in a perfectly inelastic collision, then both carts would have moved together after impact at about half of cart A's initial speed, which would have been much slower than what was actually observed. The data therefore shows that the real collision was closer to the elastic case than the perfectly inelastic case, but still lost some kinetic energy. What does it mean that momentum was nearly conserved but kinetic energy decreased? The fact that momentum was nearly conserved means that the collision still followed the main idea of the momentum principle. The motion of cart A was transferred to cart B during the short collision interval. However, the decrease in kinetic energy shows that not all of the original motion stayed in that form of translational motion after the impact. Some of the energy was transformed into other forms, such as sound, small variations of the carts and track, slight deformations, and thermal energy from friction. This is why the cart still behaved, according to momentum conservation, reasonably well. While the kinetic energy after the collision was smaller than before the collision, the result suggests the collision was partially inelastic, not perfectly elastic.